video, we want to sum up, just to summarize what we talked in the previous video before. So procedure for analysis of moment distribution. The distribution factors and fixed end moments. The joints on the beam should be identified. So there's first thing, you need to identify what type of joints we are dealing with. Once we have identified, you can calculate the stiffness factor based on the length and the EI, but EI usually remain the same based on the length. So K is equal to 4EI over L. So, and then using the value of K, you can calculate the distribution factor, dF, which is K divided by summation of K. So, you have your dF, you calculate your K, then calculate your dF. And then we also did discuss about the condition for fixed end and then end pin or roller. So, for fixed end, your dF is equal to 0. But for your end pin or roller support, so your dF will be equal to 1. So in this case, once you have you will shorten your calculation process. Once you identify the type of support, so you can straight away identify the value for dF. 0 for fixed, 1 for roller support. But if it is in between, you have two members, and not end pin or end roller. The roller is in the middle, so you need to calculate your dF. Next, you calculate your fixed end moments. So you calculate the fixed end moments for each loaded span. This want to highlight here, loaded, because if there's no loading, so there is no fixed end moment there. The moment will be distributed from the loaded span. So these are determined from the table, and then positive fixed end moments act clockwise. As we talked in the previous video, positive is clockwise, negative is counterclockwise. It is important to be consistent about this straight away from the moment you calculate the FEM up until you sum up your moment distributed at each span. So for convenience, these values can be recorded in tabular form, as we showed earlier in the previous video, and similar to that shown in the figure 12-6C. And then this is on the moment distribution process. Once you have come up with your table, so assume that all joints at which the moments in the connecting span must be determined are initially locked. So first thing first is lock. So and then determine the moment that is needed to put each joint in equilibrium. Basically, we apply the opposite moment. So release or unlock the joints and distribute the counterbalancing moments into the connecting span at each point, each joint. So we unlock, and then we distribute the counterbalancing moment to the adjacent joint, connecting joint, like C to B, as we've done previously. So carries these moments in each span over to its other end by multiplying each moment by the carryover factor of half. So half of it will go to the adjacent joints. So repeating the cycle of locking and unlocking the joints, it will be found that moment corrections will diminish. It will slowly reduce over all the procedure, over the lines, until achieve its final deflected shape. So when a small enough value for the corrections is obtained, the process of cycling should be stopped with no carryover of the last moment. So basically, if it is small enough moments, and then we can stop there and then sum up. Usually it's less than 0, or sometimes we set like a 3 round number, like 3 titik perpuluhan macam lah, 0.111. Okay, so then we can stop. So each column of FEMs, distributed moments and carryover moments, should then be able to sum up all the columns, each column for the joints. If it is done correctly, moment equilibrium at the joints will be achieved. You can see at joint, for example, joint B before, there's a balance here. So next video we talk about this example